Today we have a special guest, Tom Stanley, who comes all the way from Little Rock, Arkansas, and he's going to be speaking about the harnessing the power of excess statistical significance. I could read his bio, but we've also sent it to you, so you can take a look. I guess what Tom likes to do is do meta-analyses. He also teaches a little bit of history or the odd history class he's taught in the past. He has a connection to Hendrix College and with Deakin University in Melbourne. He's since the 80s, he's been focusing on doing meta regression methods, and he runs a couple labs. Sounds like he's a very busy guy. Likes to travel to Greece and go to Athens and do presentations and meet with his colleagues there.
Thank you. I'm very grateful that you took the time out of your very busy schedules to be here with you. I'm looking forward to your questions. After several decades of being a professor at a small liberal arts teaching college, Hendrix College, and doing a little research on the side over the summers and the holidays, I was given a research position at Deakin University. There we have an interdisciplinary lab that specializes in meta-analysis. It's called DeL.MAR, by the way. Today I'm going to introduce several new meta-analysis methods, both for detecting publication bias and also for correcting publication bias should it exist, should it be there in a systematic review in an area of research. These methods are surprisingly simple. It's Statistics 101. By the way, this is joint work with John Ioannidis and Chris Kouliagos. We have a couple papers that are available about the main ideas I'm presenting today. One was published, one's not published yet. But we have an R&R for that. I'm knocking on wood that it might someday soon be published. But anyway, there's a couple papers you can download off online from it. Okay, let me summarize what I'm about to talk about today first. All these new methods are fundamentally based upon an idea of that's called excess statistical significance, or ESS for short. ESS gives us the basis for several of these new publication bias detection methods, and also for a way to correct for publication bias. It does all of those things. In particular, ESS is a necessary condition for publication bias. We prove mathematically that if you have publication bias, you should expect excess statistical significance to be positive. It's an indicator of selection for statistical significance, or SSS for short. I see this as a broader way of characterizing what's often called publication bias. We can talk about that in discussion. And it's also can be used for meta research as well. There's basically two main themes to today's talk. One is how excess statistical significance provides these new tests for publication bias. And the other theme, the other strand is about this new weighted average, which I call WILS, that greatly reduces random effects large biases and rates of false positive when there is a selection for statistical significance. So to talk about this first strand, we have these two tests. One is a test for excess statistical significance called TESS, and the other one's a test for the proportion of statistically significant tests. TESS-PSST as a acronym. Both of these are generalization of a chi-squared test that John Ioannidis and Tom Tricolinos proposed back in 2007. Both of them are ways of identifying publication bias. They're more powerful than a better known Hagger regression test and the selection models. One flavor of selection models is called 3PSM. Our innovation is to account for heterogeneity explicitly by using an estimate from meta-analysis. John and Tom's old tests, they acknowledged this, had high rates of false positives when there was heterogeneity. So it really only worked if there wasn't heterogeneity, essentially. Again, you'll get tired of hearing me say this. Excess statistical significance lies at the core of all these ideas and all these methods. So how in the heck do we calculate these things? How do we get a handle on excess statistical significance? Well, first is the idea of Esig, what I call Esig, which is the probability that study I will be statistically significant in the absence of publication bias. These probabilities are summed across all estimates in a meta-analysis, all studies in the meta-analysis, which I call K studies. Once you sum them up, it's just Esig without the subscript, and that's a total number of results you would expect to be statistically significant in an area of research if there were no publication bias. Excess statistical significance then is the difference between what we expect and what we see. It's simple as that. In order to calculate Esig, however, we need to have an estimate of the mean effect. You might not all be familiar with our unrestricted weighted least squares. Unrestricted weighted least squares, or UWLS, is the same point estimate as fixed effects, but it automatically accommodates heterogeneity by using the variance covariance matrices mathematical invariance to any multiplicative constant. We know that it's better than random effects if there's publication bias. Otherwise, they're practically equivalent. We've published 2 papers about this, one in statistics and medicine, the other one in research synthesis methods. To calculate the unrestricted weighted least squares is the simplest of all possible regressions. You simply use the standardized effect size divided by its standard error as the dependent variable, and 1 over the standard error, which is sometimes called precision, as the only independent variable. No intercept. It's very important to do this without any intercept. In any case, the estimate here of this coefficient on precision is the unrestricted weighted least squares, just your standard statistics that get reported in any kind of regression package will give you unrestricted weighted least squares. It's confidence intervals, it's t-values and everything else. Okay, so once you have that estimate of the mean effect, we also look at all the estimates of the standard errors for every study. These need to be reported. You can't calculate weighted least squares or random effects or any summary without these standard errors. In addition to that, we also use the meta-analysis to calculate the heterogeneity variance, usually called TOS squared. Then we put this in a simple Z formula, where again, the unrestricted weighted least squares is the mean, and the variance is the sum of the standard error squared plus TOS squared, of course, the square root of that, and make it a Z value. 1 minus the cumulative normal for that Z value gives us each of these Esigs for each study, each estimate. We sum up over all of the estimates, all of these studies, and we get a total number that we would expect to be statistically significant if there was no publication bias. And again, excess statistical significance then is the number that were actually statistically significant, which is SS, minus this expected number. Again, our innovation is that we account for heterogeneity. Past approaches looked at only statistical power, not heterogeneity too. So for our first example today, I'm looking at ego depletion. Ego depletion is a rather well-known and controversial psychological theory. Ego depletion is the idea that we all have a limited supply of willpower, and it decreases with overuse, famously promoted by Roy Baumeister. There was a Slate cover story about ego depletion's publication bias, and the F word was used by a Canadian psychologist, believe it or not, to describe the current state of social psychology. Well, is there any publication bias here? Any issues you see in this simple funnel graph? Well, yes, probably. And it's probably fairly obvious. But anyway, if we take these 116 estimates that reported about experiments, reported about ego depletion, we find that the median standard error is about 0.28, The unrestricted weighted least squares is about 0.34, and tau is 0.28. Tau, excuse me, 0.38. Tau is even larger than the mean. And all of these are in standardized mean differences. All of them are measured by Cohen's D. So I'm just using this as an example of how we calculate these things, excess statistical significance and Esig and all that. So you see two curves here. The blue curve is just your standard normal distribution, which you plunk down at 0 to test for a 0 effect. And of course, 196 becomes the magic number above which you have statistical significance. Nothing new there. The only new thing, I suppose, is based upon our meta-analysis estimates, we don't expect the distribution to be that distribution. We expect it to have a larger mean, about 0.35. So we moved this curve over. And also we expect it to have a higher variation, a larger variance, because there's heterogeneity, quite large heterogeneity, as a matter of fact. So the orange curve represents both sampling error. The blue curve is only sampling error. So the orange curve has both sampling error and heterogeneity accounted for that. So when you account for both a larger variance and a larger mean, the orange curve shows that about 34% of the area should be in the rejection region. And this is now just for the typical estimate, not for all of them. There's 116 of them, so I'm not going to show you 116 calculations. But so for the typical one, we expect the probability of being statistically significant is about 34%, even if there was no selection for statistical significance. When you apply that to 116 estimates, you should expect about 39 of them to be statistically significant. Instead, 51 were in fact statistically significant. So that the excess statistical significance is 12, or about 10 point something percent. Now to finish this calculation and actually show you our test, our first test is this PSST test, and it's the proportion of statistical significance test. So we convert the Esig here to a proportion, just divide it by K, and that becomes our null hypothesis. And so our null hypothesis is that the actual proportion that are statistically significant is less than or equal to what we'd expect without publication bias. And so that's what PSST here is. And so this gives the simplest of all possible hypothesis tests. This is Statistics 101. This is what you learn, about 10 weeks into the class, maybe. Well, that's assuming you have 15 weeks. But anyway, a simple z-value because of the normal approximation to the binomial. P with a bar over it is the actual proportion that we find to be statistically significant. The PSST is what we assume to be true under the null, and that comes from this Esig thing. And again, just a very simple back of the envelope calculation. And it's just a z-value. Because we're looking for excess statistical significance, it's a one-tail test, and we test against the critical value of 0.645. TEST is this test for excess statistical significance. Here, instead of looking at the proportion that are statistically significant, we look at the proportion that are excess statistical significance. ESS here is now a proportion. We look at that directly, and we compare that to yield 0.05. And so 0.05 is our null hypothesis. So again, we get a pretty much the same kind of calculation, except ESS now is our observed proportion, and we test that against yield 0.05. TESS-PSST is now a combined test. If either one of these two z-values are statistically significant, we consider this evidence of publication bias. And I guess that's all really to say. Simulations show that this combined test, the individuals ones as well, they all have low type 1 errors and high power relative to the alternatives. And the best considered alternatives are the Hagger regression and 3PSM. And speaking of those, here they are. Hagger regression simply is a simple regression of the observed effect size, which I'm calling DI here for Cohen's D, against its own standard error, SE. The regression coefficient here, gamma 1, the test of that is a test for publication bias. Please use On the weighted least squares here, where 1 over standard error are the weights, 1 over standard error square is the weights. This comes from Hagger et al., a group of medical researchers. Don't use random effects on this. Please do not use random effects on this. Anyway, this is widely known to have low power. It's a nice test. It's just not very powerful. Everybody recognizes that. 3PSM is the 3-parameter selection model. There's a lot of different flavors of these selection models. They originally came from Ivangard and Greenhouse back in the 80s, but Hedges has a number of these, and Hedges and VIA is probably the dominant strain that's still remaining. All of these selection models estimate using maximum likelihood the relative probability that a non-significant result will be reported, assuming that this probability is constant. We show that 3PSM breaks down that this probability is not constant, and we know in applications that it's not going to be constant. Okay, returning to the ego depletion results. Random effects has an effect of 0.43, nearly a medium-sized effect. The unrestricted weighted least squares is 0.35, as already mentioned. There's been a large-scale replication that found no effect here for ego depletion. Thus, we know there's a lot of publication bias and hence selection for statistical significance. We observed in these 116 estimates that 45% of them were reported to be statistically significant. We would expect only 34% of them to be statistically significant, giving excess statistical significance to be 10.7%. When you apply these numbers to those 2 Z formulas I showed a minute ago, you get either 243 or 283. Both are statistically significant at the 0.01 level. 3PSM here is not statistically significant. The Hagger test is. The Hagger test, even though it's not supposed to be very powerful, it's plenty powerful in this application. So of course we do simulations of this. I call our simulations evidence-based because they're grounded on the actual value of key research dimensions from large surveys of psychology. They were pre-registered back in 2019, and many of the results were already posted way back in 2019. And these simulations reproduces the sizes of biases and the shrinkages we see in large-scale replications. Here, when we apply this to these new tests, they show that these new tests have acceptable type 1 errors and high power to detect publication bias. Here's the type 1 errors. I've highlighted the average. All of them are under 0.5, except for Tom and John's chi-square test. But again, it's known to break down when you have heterogeneity. Oh, by the way, in psychology, typical heterogeneity has a tau value of about 0.3. We did a big survey of this. There's lots of variation in heterogeneity, but typically, if you want to know what's usually the case in psychology, look at the 0.3 values. Anyway, everything works out pretty well except for IT, but there's nothing new there. When we look at the power of these tests, in this case, we have just 20 studies, and I'm assuming that there's 50% of them have been selected to be statistically significant. By the way, you need this 50% selection if you want to reproduce what you see in large-scale replications. But I'll come back to that issue if you don't believe it yet. Our methods here are at the top in terms of power. 3PSM and PSST are about the same at the second level there. You can't necessarily see 3PSM because it's kind of hidden behind it. It's TESS that's the higher power one. And you notice the Hagger regressions are at the bottom, which is typical what we're going to see consistently. Also notice that power here, with only 20 studies, is over 70%, which is actually pretty darn good for these kinds of tests. Here we have just 10 studies, and now power for our methods are down to about 50%, but still I think that's pretty good. You see more clearly 3PSM is a bit lower, and that's with just 10 estimates. In this case, we're assuming we have 25%, or just 1 out of 4 studies have been manipulated for statistical significance using questionable research practices or whatever. somehow selected for statistical significance. But now I assume we have 80 of these studies, and power of our methods are still pretty good, almost 70%. 3PSM was almost as good and is as good if heterogeneity is really low, but its power falls quicker with higher heterogeneity than our methods. But there we go. In all cases, our methods dominate 3PSM and also the Hagger regression. Here's another example. It's nicotine replacement therapy. And there was a large Cochrane systematic review that concluded that nicotine replacement increases the rate of long-term quitting, that is quitting smoking, by approximately 50 to 70% regardless of setting. That comes from Steed et al. When we looked at this data, we found that when you account for both risks of bias and publication bias, there's virtually no effect of nicotine replacement therapy. And here's just a graph of those randomized clinical trials. Again, I would ask, but there's too many of us, is there publication bias here, or what do you think? And it's maybe it's clear, maybe it isn't clear. It doesn't matter. We have tests for these things. So there's 122 of these randomized clinical trials. The random effect estimate here is, again, about a medium-sized effect of 0.47. Oh, I shouldn't say that. These effects are in the logarithm of risk ratios, not standardized mean differences, excuse me. The unrestricted weighted least squares is just slightly less. When there's a lot of publication bias, that's what happens. Unrestricted weighted least squares is always better, but not necessarily a lot better. Unfortunately, in this case, our methods and also 3PSM do not find evidence of publication bias. They both have larger p-values. I brought this case up on purpose because I just wanted to emphasize that our methods are still a very conservative test, because it uses an estimate of the mean, and this estimate of the mean is known to be biased if there's publication bias. So the higher the mean is, the higher the probability you find a statistically significant result, even if you don't have publication bias. So this makes it more difficult with a biased mean. It makes it more difficult to find evidence of publication bias. So that's one of the restrictions of this method. But those simulations accounted for all that. So there's nothing new there. And unrestricted weighted least squares is at least less biased than random effects. That we really have a lot of evidence for. So I would recommend, with any doubt or in all cases, instead use a slightly different estimator, which we call WAP, which is the weighted average of the adequately powered. We published a paper in Statistics in Medicine on this, and it's simply the same unrestricted weighted least squares, except it's calculated on only those estimates that have 80% power or higher. If you use the WAP instead, our PSST test comes out to be statistically significant, and we see evidence of it. By the way, when you slice this data by risks of bias, there's really clear evidence of publication bias here. But anyway, just another example. So in this case, to summarize these tests for publication bias, the simulations show that they outperform both Hagger regression and 3PSM. And 3PSM in different simulations that I'm not reporting right here today are even worse if you allow for this probability that a non-significant result is published. If you allow it to be not constant, if you allow it to vary, it breaks down. And I would argue in practice, we know that it's not constant. As I've already said once or twice, this idea of excess statistical significance is also going to lead to new ways of correcting for publication bias. I call this new weighted average WILS, which is the weighted and iterative least squares. Again, it's a simple weighted average. In fact, it's exactly the unrestricted weighted least squares, but it's an unrestricted weighted least squares after you discard those estimates, those studies most responsible for excess statistical significance. Once you do that, we can show both comparing it against replications and comparing against simulations that it greatly reduces bias and mean squared error at little to no cost to efficiency. Also, advantage of this simple weighted average, it makes no assumption about the flavor, the mechanism of the selection process, and it can't be dismissed as a small study effect because there's no privilege given to small or large studies, and there's no assumption about a correlation between effect size and standard error or sample size or anything like that. It makes no assumptions about any of those things. Okay, so how in the heck do you calculate this simple weighted average? Well, again, the first step is you start with this unrestricted weighted least squares, and you calculate the residuals from this. Any regression package will automatically calculate these residuals, and I call them EIs. After that, you go ahead and calculate excess statistical significance, and that's calculated in the same way we discussed using equations 2 and 3. You take the value of excess statistical significance, you round it up, and this is going to tell you how many studies you should drop. Okay, that just tells you the number of studies you should drop. Which studies you should drop? Well, after you know how many you should drop, you drop those with the largest residuals. You know, if it tells you 5 studies should be dropped, then you drop those 5 studies with the highest residuals. And then you repeat this process over and over again, each time dropping those studies with the highest excess statistical significance until there's no more excess statistical significance. The last estimate you get, that is the last unrestricted weighted least squares estimate you calculate through this process is what we call WILS. I mean, it is the unrestricted weighted least squares again, just calculated on a reduced number. Well, it doesn't have to be reduced. Often you won't find excess statistical significance, and so they're the same thing because you don't drop any studies. What we want to do next is we want to compare WILS to all cases which we can find where we know what the true population mean is. There's basically 2 situations where we know the true population means. Besides simulations, and we were going to show these, where you control the true population mean, we have large-scale pre-registered multi-lab replications. And these are probably preferred to simulation because they deal with real research. And so the conditions of real research might be different than how you simulate them. They're widely considered to have little or no publication bias or to use questionable research practices. They use very large samples. They're very accurate. They're very powerful. Carnarvon et al. Did a systematic review of all these PMRs that were related to a meta-analysis where they could match to a meta-analysis. And they published this in 2020 in Nature. And they did all these calculations of random effects, also 3 corrections for publication bias, our pet piece, 3PSM and trim and fill, they did all that. To this, we went ahead, used their data and calculated our WILS just for comparison. 15 meta-analysis, a lot to compare here, probably too much to put in one table. So let me just summarize what that table says. And this is also what Carnarvon et al. Report. When compared to these replications, random effects is quite a bias, 0.26 Cohen's D, 100% falsely positive. Trim and fill, really no better. 3PSM, maybe, yes, a little bit better. At least its false positive rate is less than 100%. That's good. Our WAP, by the way, is virtually the same as 3PSM in this application when compared to large-scale replications. Our pet piece is a whole lot better. It has negligible bias, 0.05 is nothing, and a false positive rate of 14%, a whole lot better than 100%. WILS is virtually the same as, I mean, it's not the same, but overall it's virtually the same as pet piece. And it has a 14% false positive rate if you test WILS at 0.01. And I know that's a little wrinkle. I'll come back to that in a minute. But so just to summarize, when we compare to WILS to these large scale replications, we find a random effects, trim and fill, 3PSM, they all have notable biases with high false positive rates. WILS and pet piece are a whole lot better. So again, simulations is what we want to do. Same simulation designs, pre-registered, evidence-based. Our designs reproduce what we see in these same these same large-scale pre-registered meta-replications. We find with WILS, there's a small, often practically negligible bias, virtually nothing. Much smaller mean squared errors if there is selection for statistical significance, much lower type 1 errors if there's publication bias, much better statistics than random effects. Okay, so some graphs instead of a bunch of tables to show this. This is the bias. We assume we have 80 estimates. We assume the true mean effect, we can control it, is 0. And there's 50% selection bias. Again, we need to assume 50% selection bias if we want to get the same size bias we just saw in these replications. And notice that random effects has the highest bias. Again, at the center here, its bias is almost exactly what we saw in these large-scale replications. As we would expect, unrestricted Whaley square is at least a little bit less biased. hetPS is a lot less biased, but its bias increases with heterogeneity. And WILS is at the bottom, virtually zero bias. I mean, it's not zero, 0.01, 0.02, something like that. But practically speaking, that's no bias. False positive rates, type 1 errors, 100% for random effects and the unrestricted Whaley squares. hetPS is a whole lot better, WILS better still. However, if you test WILS at 0.05, it does have slightly inflated type 1 error. So if you're worried about that, test at 0.01. Mean squared error, which counts for both efficiency and bias. Random effects is way the heck up there. WILS is way down there with everything else in between. Not really surprising. So to summarize WILS then, it does a really good job when compared to random effects and 3PSM. They both have unacceptable rates of false positive and notable biases. WILS lose little, if any, efficiency in actual applications. Often WILS has a smaller standard error than random effects. It's not perfect. It's just a simple weighted average. Its type 1 errors are a bit too high, and it does, in fact, tend to underestimate medium to large effects. I mean, it's throwing away estimates, and so it does so falsely sometimes, and that tends to underestimate those medium to large effects by about 10%. I don't think that's a big handicap, but we can talk about that in discussion. Random effects is only better if there is no selection for statistical significance, but we never know that. We never know that. And it often, I find, not always, but probably in over half the cases, there's some selection for statistical significance. Oh, by the way, medicine is much better. Medicine is much better. WILS assumes nothing about selection, therefore it's not limited to any particular selection mechanism and can't be dismissed as a small study effect. Okay, I'm almost done. To say really briefly, excess statistical significance can also be used in meta research. Like in these big studies of publication bias across the disciplines, it can use as an outcome, as one measure of publication bias. We have one of these undergoing right now with a group of psychologists. Yes, we have Cochrane database in there, a large database of economics, of psychology, political science, I think a couple other smaller disciplines. I actually don't know what it says yet. It's very much a work in progress. We also can use this to evaluate some of these transparency and these policies to try to make our science a little bit better. We have a study with, knock on wood, with an R&R, we're currently revising it with Krista Kouliagas, that evaluates mandatory data sharing policies at the top economic journals. And we show quite notable effects there from mandatory data sharing. And excess statistical significance is one of our outcome measures. Also just the t-values, how significant results are is another outcome measure. Yeah, we're just have to be hopeful. So in summary, can ESS cure SSS? Of course not. But ESS can help identify and treat publication bias. We have these papers, as already mentioned. Thanks for your attention. I look forward to your comments.
So one question came in, is there any limitation on the application of ESS for study design, for example?
Not that I know of. I mean, I assume that he had RCTs or something like that in my simulations, and I've only applied it extensively to experiments in psychology. I think that the TESS-PSST stuff is going to be really highly robust. I don't have any concerns about it whatsoever across design. WILS, I mean, I should be more modest about WILS. It's just a simple weighted average. I think it will work across designs to reduce publication bias. To reduce it to nothing, that's hoping too much.
Mm-hmm. Tell me just briefly, why do you choose psychology as a sort of area that you focus on at the beginning? Why psychology,
well,
as opposed to other disciplines or other fields?
Well, I'm an economist,
Yeah.
and I've applied this stuff to economics. Economics has a whole lot of publication bias. Economists are slower to the party of both meta-analysis and certainly to publication bias. Although some of our top journals now are publishing papers about these things, but they don't want to know about their. Oh yeah, hi James. I'm not too sure they want to know about their dirty linen. Okay, why? I think medicine is different. I have done simulations where I try to do medical research, and I work with John, somewhat with John. And so but my knowledge of medical research is this much, and it's kind of overwhelming. I mean, the Cochrane database is overwhelming for me. I work with people like James, who are better with those big databases, and we're looking at some of that stuff now. I don't think publication bias is nearly as big of a problem in medicine. That's my take. I think John would disagree with me. He thinks it's still a big problem there. Yeah. So anyway, psychology has all these replication, crisis going on. So I think that's why I led there, because we now have what's going on in replications, and there's a really big movement for that that's revealed some of these things. So that's why I moved to psychology in effect. So I can test these methods out where we have another, kind of realistic baseline to compare against.
Good. So a question from your friend James says, can you comment on the idea of using TESS-PSST with the UWLS estimator for the mean versus WAAP estimator for the mean?
Excellent question, James. I know James.
He adds, let me just say, there seems to be some analytic flexibility there that might leave folks unsure about how to proceed.
I would proceed with the WAP if that's reasonable. The WAP assumes that you have some adequately powered studies. Now, the way we do WAP, it defaults automatically to just unrestricted weighted least squares if you don't have adequately powered studies. So that's in our paper, we automatically default it to just the weighted average, the simple weighted average. So I mean, but that's also a matter of, I guess, judgment. But I would use WAP for it. I didn't put that in the original paper because that adds another layer. Maybe that's controversial. I mean, a weighted average, which is the same weighted average as fixed effects, is not controversial. So that's why I did that. Now, I've actually already done some simulations. I'm also done some simulations on using WILS itself to be the estimate in order to do TESS-PSST. I mean, that's sort of circular, but you can still do that. And yeah, it doesn't really work that well. WILS really reduces the bias. And when you really reduce that bias that much, you're going to get inflated type 1 errors for these other methods for determining whether or not there's publication bias. So I think WAP hits the sweet spot.
Good. So a question from one of my colleagues, Malcolm McClure, asks if you could show us again the slide for the nicotine replacement and maybe talk us through which data points would get dropped by your methods and maybe contrast it with other approaches.
I don't know which ones would get dropped. I hadn't actually looked at that. I guess I can try to do that.
Excellent. We're there.
I think that's probably large enough for now anyhow. Yeah. So the results that are far to the right, those might be the ones that are going to be give you larger t-values that tend to be exaggerated and tend to be excess statistically significant. Also, the ones that are both towards the right and a little bit higher are going to be the ones. So, well, I guess I can point. I mean, I think a point like that, definitely that point, is going to have a high residual. I don't know how many of these points will. Some of them might not even be statistically significant. The ones down here, but I mean, statistical significance probably hits, something like that. And anyway, it's going to be the ones to the right and also the ones up. So they're the ones that are kind of unusually to the northeast. I actually didn't look if the two top ones get thrown out. I doubt if they do, because I think they're the ones that it's going to influence the overall weighted average the most. But you could throw out some of the top ones if the bulk of the estimates were, further to the left of them.
And how does that contrast to other approaches?
Well, the whole contrast is with the focus on excess statistical significance. Yeah. And we can calculate that, and we can look at which studies seem to be more inflated in terms of, how a statistically significant result when they had low power. Basically, it's looking at whether something's reported to be statistically significant and what its power was. And if its power is really small relative, to being statistically significant, and yet it's statistically significant, that's just simply a more questionable study.
Just another comment from James. He says, I think you could visualize this by drawing funnel contours.
Yes.
The outliers are the ones with the largest Z or Z statistics. So the furthest out in the funnel around the null.
Kind of, yes. I didn't put the contours in here. He's exactly right. Of course, James would be exactly right. But I would say it's the one kind of the furthest to the northwest. Excuse me, northeast. Because that's standardized. And so higher precisions that are kind of away from that contour are also going to be weighted highly in terms of being a residual. So both up and to the right, so kind of towards the northeast are the ones furthest to the northeast from the contour, which I didn't put in there.
Sorry, I got it now. Good. So at one point you said there was small study approach. Do they just do a horizontal line and drop the low ones?
Oh, it's not a small study approach.
I want to. I get what you're doing, but I'm so ignorant about these different approaches. I wanted you to maybe contrast yours. So you're. It's like if I were ignorant, if I have a general idea of meta-analysis, but I get lost in all the math. I say, well, when I look at this, I can see I get the general idea that there's bias in small studies, and I can see it. And so I think I'm going to snip off all the ones that I think are out to the right until it looks more symmetric. And now that's just a extremely rough subjective approach, and obviously a mathematician who specializes in probability will be able to do a much better job at snipping. But I'm interested in, and some people would say, well, the easiest thing is just draw a horizontal line halfway up and ignore all the small studies. Well, that's really dumb because you're throwing out a whole bunch of information. But I'm interested in what some of the other main methods would do. Do they not throw studies out, but they try to keep them in and just weight them differently? and does your method re-estimate the mean every time you throw things out?
Yes.
So you're sort of, so it's pretty, in some ways, it's pretty common sense. It's sort of saying, well, you know, we all agree this should be symmetric and that there are biases there. So let's drop one and see what it looks like again. And let's drop another and see how it looks. And if you do that with good math theory, you should end up with a more symmetric distribution that has the less bias in it. And I guess one of the things interesting is
thanks for summarizing my idea. You did a perfect job.
So even though some of us are trained to have an aversion to statistical testing, and the word significance even. And so when you talk about excess statistical significance, I sort of cringed at the idea, oh goodness, is this going to be overemphasizing p-values and all that sort of stuff? But actually, you are focusing on estimation, right? The mean. And
we're trying to correct for that. The excess statistical significance exists without us.
Right.
Those studies are claiming
it is a kind of parameter.
Those studies are claiming to be statistically significant. That's not on us.
Right.
We're trying to fix that.
And excess statistical significance is a kind of parameter of publication bias, right? It's a real thing, and you're trying to, at the same time, estimate it and then adjust for it.
That's it. You asked about 47 questions. Yeah.
Malcolm's like that, yeah.
There are many other approaches to this. You kind of walk through trim and fill. Trim and fill is the idea, you whack them off and then you put them back in. It's a terrible idea. There is a trim and fill method. It's very popular. It was the most popular method both in medicine and in psychology for a number of years. Other meta-analysts, not just me, but pretty much the methods community have run away from that method. I joined a group of medical researchers way back in 2009, Moreno et al., Alex Sutton, and they did it. I didn't do it. I was just one of the co-authors. They did a comprehensive simulations, and they were pro trim and fill, and they found trim and fill just doesn't work. It's really bad. I mean, it's a good idea. It's just how do we identify those and identify them accurately? Now, the Hagger regression sets up another method, and it looks at simply a correlation between effect size and SE. And that's another method to correct. Well, we invented a method called PET-PSST, and that would take several slides and some explanation, but that's one of our methods, and it works quite well to correct for publication bias. As Carnarvon et al. Said, it's often criticized by medical researchers that it assumes away that there's a small study effect. They're saying it just looks at a small study effect, and small studies can be better than large studies. So why are you picking on small studies? And so it's often dismissed because it looks at a correlation between, in effect, the size of the study and bias. And I still like the method. It has limitations, and hence that's why I look for other methods that don't have those limitations.
It sounds like trim and fill was this effort not to throw out studies, but to move the points. Is that right?
No, it's trim. You throw them out on one side, but maybe that's not the best approach. So you also fill. So the ones that are missing on the other side, you fill those in.
Oh, that's really bold.
And you can do one, the other, or you can do both, whatever you want.
I can imagine being someone who really worked hard on a study that turned out to have a publication bias, and you throw it out and feeling rather peeved. But no, it is interesting that that basically the field has the confidence to throw out studies completely, rather than to try to I don't know. The Bayesians are going to come along and say there's got to be a Bayesian approach to this. I don't know.
We're working with Bayesians on a different estimator, as a matter of fact.
Okay.
Yeah.
Anyway, thank you very much. It really helps to understand. The math was kind of daunting, and I guess it's recorded so we could go through it too. So, but it really helps getting a sense of that it's a kind of progressive dropping of outliers with a very carefully tested probability algorithm, and simulations show it works.
Okay.
Thanks.
You're very agreeable. Okay, I think we're almost at the end of our time here. We might have 30 seconds for any last comments or questions. Somebody put in, James, do you have any reference for the one to learn on the Bayesian aspect? So James put in the chat that there is definitely work on Bayesian analogs of selection models. So maybe yeah.
We're working with a group of psychologists on this. Franishek and Max Mayer and Wagon Makers. We have a nice combination of selection models in our pet piece in a Bayesian model selection basis. That's an ongoing work. We have an R&R for that. I really like that. That's a way of taking several of these approaches and averaging them out.
Excellent. Okay, I think with that, we'll end today's session. Tom, again, on behalf of the Therapeutics Initiative, thanks a lot for joining us. Fascinating talk. Thank you for the questions from our audience, Malcolm and others, and everyone have a good day.
Thank you. Okay. Bye.